Okay, so today we're going to solve Euler equations. So what are these equations? Well, these equations are very special because they have a very specific form. So these equations, they would look something like this. So you have some alpha x squared y double prime plus beta x y prime plus gamma y equals to 0, where alpha, beta, and gamma are going to be real numbers. Okay, so you have function x squared with y double prime, x with y prime, and constant with y. If you have it in this specific form, then we're going to assume that the solution form, it's going to be the function y is equal to x to the r, where r is the root of this equation. So once you plug in this solution into the Euler equation, you will have this polynomial. So it will reduce to this polynomial equation, which would be alpha r times r minus 1 plus beta r plus gamma equals to 0. Now the question is, what are the roots to this equation? Well, because this is going to be a second order polynomial, we know it can have 3 different scenarios for the roots. So our solution can look as follows. So our function y of x, it's going to look in 3 different forms. So if the roots are real and distinct, so say, let's say r1 is not equal to r2, and they're both real, so our solution is going to be y, well, I already have y outside. It's going to be c1 x to the r1 plus c2 x to the r2. So that will be the solution if the roots are real and distinct. Now, if the roots are, say, equal to each other and they're real, so r1, r2 are real, then we know the solution is going to be c1 x to the r1 plus c2 ln of x times x to the r1. Now, I didn't really write down the absolute values here. Let's just assume that x is greater than 0 so that we can remove the absolute value. But if you do want to put in the absolute value around all the x's we have, feel free to do that. Now, the third case we can have would be, what if r is a complex root? So we can say that r1 and 2 are complex conjugates, so say a plus and minus bi. So you have a complex root. So that means our solution now is going to be c1 x to the a times cosine of b times ln of x plus c2, so I'm running out of space, so let me just write it underneath here, plus c2 x to the a times sine b ln of x. So that will be the solution if the roots happen to be complex roots, okay? All right, so let's get started and let's see how the solution will look like for our first example. So here is our first example. So say we want to find the solution to the example 2x squared y double prime plus 3x y prime minus y equals to 0. So in this case, we're going to go ahead and identify alpha, beta, and gamma. So alpha happens to be 2, beta is 3, and gamma is -1. So that way we can write out the polynomial equation to this. So we have alpha times r minus 1 plus beta times r plus gamma equals to 0. And then we plug in our constants, alpha, beta, and gamma. So we have 2r times r minus 1 Beta is 3, so that's 3r, and gamma is -1 minus 1 equals to 0. And now we just solve this polynomial equation. So we have 2r squared minus 2r plus 3r minus 1 equals to 0, which will simplify to 2r squared plus r minus 1 equals to 0. And now we can go ahead and try to factor this. So this can be factored into, let's say, 2r and r. And now we can try to factor this. This can be factored into, let's say, 2r minus 1. And then I can do plus 1 here. Will that work? Yeah, looks like this will work. So we know our roots are r1 is equal to 1/2, and then r2 is equal to -1. So if these are the roots, then our solution to this Euler equation will be in this form we have right here, c1 x to the r1 plus c2 x to the r2, because our roots are real and distinct. So we have y of x is equal to c1 x to the 1/2 plus c2 x to the -1. So that would be the solution to this equation. Okay, great. So now let's do another example. Let's see, we can solve another Euler equation. So let's work out this example. So say we want to find solution to x squared y double prime minus xy prime plus y equals to 0. So here's another Euler equation in that form. So we know alpha is 1, beta is -1, and gamma is 1. So we know our polynomial equation would be alpha times r minus 1 plus beta r plus gamma equals to 0. And then we plug in these constants. So we have 1r times r minus 1. Beta is -1r, so -r plus gamma, which is 1, equals to 0. And then we try to simplify this. This will give us r squared minus 2r plus 1 equals to 0. And this can be factored into r minus 1 and r minus 1, which is just r minus 1 squared equal to 0. So we can see that this has a repeated root. R1 is exactly equal to R2, which is 1. So in this case, well, let's check. In this case, our solution is going to be case number 2, where you have c1 x to the r1 plus c2 ln of x times x to the r1. So we're going to write that out using these roots. So we have our solution to this. It's going to be y of x, which is c1 x to the 1, well, let's just say x, plus c2 x ln of x. So that will be our solution because the roots are not real and they're repeated. So let's go ahead and do one more example so we can illustrate the third scenario we had on the solution. So let's say we want to find solution to this example. We have x squared y double prime plus 5x y prime plus 9y equals to 0. And then identify alpha and beta and gamma. So alpha is 1, beta is 5, and gamma is 9. So we have alpha r times r minus 1 plus beta r plus gamma is equal to 0. So our alpha is 1, so we have r times r minus 1. Beta is plus 5r, and plus 9 equals to 0. All right, so this can be factored into, let's see what. So we have r squared plus 4r plus 9 is equal to 0. Okay, well, looks like we can't really factor this. We're going to use the quadratic formula to find r. So r is going to be negative 4 plus and minus square root of 4 squared. That's 16 minus 4 times 1 times 9 all over 2 times 1. So that's the quadratic formula. So now we have, let's simplify inside the radical. So we have negative 4 plus and minus a square root of 16 minus 36 over 2. And then we can do 16 minus 36 first. That would give us negative 20 inside the radical. So we have negative 4 plus and minus square root of negative 20. And we see that that's a complex root. So then I can simplify this. So this is negative 4 plus and minus. I can pull out an I. So I have a square root of 20, which can be broken into 4 times 5. 4 will come out as a 2. And square root of 5 in there, all over 2. And that can be simplified completely. So our r, 1 and 2, are equal to negative 2 plus and minus square root of 5i. So those are the roots. So here we can identify which one is A and which one is B for the complex solution. So this is our A, and this guy is our B. So our solution, we know it's going to be y of x is equal to c1 x to the A cosine of B ln of x plus c2 x to the A sine of B ln of x. And then let's just plug in A and B into the solution form. So our y of x, it's going to be c1 x to the negative 2 cosine of a square root of 5 ln of x plus c2 x to the negative 2 sine of b, which is a square root of 5 ln of x. So there we have our solution when the roots happen to be complex numbers. All right, so those are the 3 different scenarios you can run into when you're solving Euler equation. I hope you enjoyed.